Hey there! We're about to summarize what we've learned in Chapter 1 of College Physics, Introduction to the Nature of Science and Physics, which is an introduction to what? Science is about what we can measure, what we can show and verify by measurement. And when we know how to measure basic physical quantities, what we can start to do is use these measurements to make approximations, estimations, and dimensional analysis, which we are going to see will involve constructions of higher level types of dimensions that are constructed from our base dimensions. But our base dimensions are what? What are those? When we're talking about base dimensions, what we're talking about are the most basic quantities that we can measure that can only be defined by how they are measured. And some of the most basic of those is mass, length, and time. Mass, length, and time. These are quantities that you can definitely only define by how they're measured. So length is what you measure with a ruler, mass is what you measure by its force interaction with another mass, and time, well, that's what you measure with a clock. Okay, SI base units are going to be meters for length, seconds for time, kilograms for mass. So here we're coming towards a problem. Measurement and uncertainty. Let's consider measurement and its uncertainty by verifying the basic dimensions of boys' copy paper as specified by the manufacturer. I think we can all agree that there's uncertainty inherent in any measurement that we make. In this problem, verifying the dimensions of Bose copy paper as specified by the manufacturer, by considering the uncertainty of our measurements, we'll be able to show that it is this uncertainty itself that's driving the rules for significant figures. That is, the rules that tell us how many significant figures we should be able to keep in a measurement and in derived values calculated from those measurements. So one of the first things we could try right here is just to verify that these 8.5 and 11 pieces of paper are equal to 216 by 279 millimeters. Let's go ahead and verify that 8.5 inches is equal to 216 millimeters. To do that, what are we going to use? A conversion factor. That's a conversion factor, I remember. 1 inch is equal to 2.54 centimeters. Let's use that to verify this relationship. I want to show that this 8.5 inches is equal to 216 millimeters. So let's use the conversion factor. So we use the conversion factor in this form. Form I like to call a magic 1. See, if I take this equation over here and divide both sides by 1 inch. So 1 inch divided by 1 inch is 1. 1 is equal to 2.54 centimeters divided by 1 inch. That's what I call a magic 1. When I multiply it by 8.5 inches, what happens? Inches cancel with inches, and we're left with, so we got 21.59, obviously, centimeters. But what are the rules for sig figs? What would they tell us here? Well, this is a conversion factor, actually. So in a conversion factor, you can assume that there's really unlimited sig figs, even if they're not. But what do we have? We really have 2 sig figs. I'm going to go ahead and break the rules for sig figs right away, just to correspond with what we got there. Round this up, and you can see when I round it, this is going to be 21.6. It's equal to 216 millimeters. Since centimeters is 1/100th of a meter and millimeters is 1/1000th of a meter, you can easily see that to go to millimeters, the conversion's super easy. Just move the decimal place once to the right, and you go straight to millimeters. Okay, so we verified that. And we could similarly verify that 11 inches should be 279 millimeters. But let's not do that. Let's go on with the rest of the problem here. That is, the problem is to verify that the density of the paper is 75 grams per square meter. I looked this up online to figure out that that's what they mean right here. Let's continue on with that. Density is an example of a derived quantity. That is a physical quantity that's derived from base dimensions, in this case of mass and length. Density is defined to be the mass of an object divided by its volume. And density is a very useful way to characterize compounds and elements. For example, the density of water is 1,000 kilograms per meter cubed, which is equal to 1 kilogram per liter, or 1 gram per milliliter. What about lead? Lead is about 11 times more dense than water, so that means it's going to be 11 kilograms per liter or thereabouts. So if you were to weigh a liter cube of metal, and it say weighed 4 kilograms, could that be lead? No. Maybe it's some sort of aluminum alloy or something like that, but certainly not lead. In our case, we want to verify the paper density as specified by the manufacturer. So in this case, we want to verify that the paper has a density of 75 grams per meter squared. And what we have here is an area density. More fundamentally, density is defined as mass per volume, because any real object, including a piece of paper, is going to have mass and volume. However, this piece of paper has a dimension that we consider ignorable, right? It's the thickness of the paper. Since the thickness of the paper is ignorable, it's better to specify the density of the paper as an area density. It's mass divided by its area, or mass per area. So let's go ahead and verify that our paper has an area density of 75 grams per square meter. To estimate the area density of our paper, one thing we're definitely going to need to know is the weight of the paper. So let's see, how are we going to measure that? Well, we're just going to put it on a scale right here, like I did. You see, I just took that whole stack of paper, put it on the scale, and measured it with this scale. And I can see that my measurement is 2.3 plus a little more. There's a little more associated with the fact that it's a little past the 2.3 tick. But how much past is it? Whenever we measure a physical quantity, there's uncertainty associated with that quantity, whether we state it or not. So the physical quantity we just measured was the total mass of the paper plus the wrapper around it. And I estimated it to be 2.31. 31 is kilograms. Now, really what I'm measuring, anytime I measure something, like this total mass, what am I really saying? I'm really saying I'm giving you my best guess, or maybe an average is my best guess. I've made a bunch of measurements and took the average, or I just made one measurement and saying, okay, that's my best guess, so I put the over bar to show that's what I mean. And then, whether I state it or not, there should be plus or minus some uncertainty. So plus or minus some, I'll just call it delta M, or maybe delta MT, uncertainty on this total mass. Okay, so there should be plus or minus some uncertainty on this measurement. What is that? Well, if I don't state it, if I just write down some number, like let's say I measure a length of something, x equals 2.1 centimeters. If I don't state any uncertainty, then I could use this rule of thumb. I could go, okay, the rule of thumb uncertainty is that it's 1/2 the least tick, or 1/2 the smallest division on your measuring device. The implication here is that this is a basic rule that measures to the nearest tenth of a centimeter. So the implication here is that this is 2.1 plus or minus 1/2 the least tick, 2.1 plus or minus 0.05 centimeters. What is the least tick for the measurement we just made of the total mass? Well, if you look back over on the scale over there, and let's say if the way I'm implying it right here is the least tick would be 0.01 kilograms. But if we go back and look at the scale we would used, you could see for yourself that really that least tick was 0.05 kilograms. So our delta MT is going to be the least tick, 0.05 kilograms divided by 2, rounded because there should only ever be one sig fig technically in an uncertainty, gives us 0.03 kilograms. Thus, using the actual least tick on our measuring device, I would say that our measurement is 2.31 plus or minus 0.03 kilograms for the total mass of the paper. To get the actual mass of the 500 sheets of paper, it's pretty clear we're going to have to subtract the mass of the wrapper. Okay, so how am I going to get that? Well, I just crumpled it up and threw it on this digital scale and found that the mass of the wrapper, which I'll just call MW for mass of the wrapper, it's equal to 19.4 grams. Now, is there an uncertainty associated with this measurement? Absolutely. Even though it's a digital scale, there's some uncertainty associated with it. Since I'm not sure what that uncertainty is, I'm just going to go ahead and say it's given by the rule of thumb. That is, the uncertainty is 1/2 the least tick. So here the least tick is 0.1. 1/2 of 0.1 is 0.05. So our measurement then is 19.4 plus or minus 0.05 grams. Now, to get the mass of the 500 sheets of paper, what we're going to need to do, we'll call that M. What do you think we're going to need to do? We're going to have to take the total mass and then subtract the mass of the wrapper. Pretty clear. How do we handle the uncertainties? Let's think about that. First off, to do this calculation, that is to subtract the total mass, to subtract the mass of the wrapper from the total mass, we're going to have to get both of these in copacetic units, right? So this guy is in grams, this guy is in kilograms. Which one's the easiest to convert? I don't know. I'm feeling like going from kilograms to grams is pretty easy. This K, what does that really represent? That K really represents a 1,000 or a 10 to the 3 in there. So if you just literally replace this with 10 to the 3 or 1,000, that will give us the mapping we're looking for, or the conversion. Just move the decimal place 3 times. So we converted the mass in kilograms to grams. So we can see this is 2,310 plus or minus 30 grams for the mass of our paper with wrapper, plus subtracting the mass of the wrapper here. Notice the uncertainty on the mass of the wrapper is so much smaller, right? This is 0.05 grams compared to 30 grams. And since these are uncertainties, plus minus, it really shows that when we do this calculation right here, this guy's driving the uncertainty. We can just drop him altogether, right? Just cross him out and just keep this guy now as our uncertainty. He's really the one holding the juice. So let's go ahead then and do this calculation. I'm going to use my calculator. So once we're done with the calculation, and then we see what we get. 2,290.6 plus or minus 30 grams. And now here we can see that this 0.6 here is really not a real thing, right? This plus or minus 30 grams is telling us how many sig figs we can really keep in our calculation. So even more properly, I think at the end of the day, I should report 2.3 plus or minus 0.03 kilograms. According to Bose, is 5 pounds. Now we need to verify that. To do so, what do we need? We're going to need a conversion factor. So I looked this up in a table. On the surface of the Earth, 1 kilogram is equal to 2.2 pounds. We use the conversion factor this way, put pounds upstairs, kilograms downstairs. Using this conversion factor, kilograms cancels. We're left with pounds. So here at the end of it, I came out with mass is equal to 5.04 plus or minus 0.07 pounds. All right, we measured the mass of the paper, and so we're well on our way to calculating the density of the paper, the area density of the paper. So what else do we need to know? Well, one thing we need to know is the width and the length of the paper, right? Because to calculate the area of the paper, that's going to be equal to length times width. So here what we're going to do is measure the width of the paper. I measure it like this. I put the 1 centimeter tick mark over here on the left side of the paper. This is the proper way to use a ruler. You line up a main division with the edge of what you can see. It helps your eye work better for measuring stuff like this. Then what you measure is the delta. So whatever I read over here minus the 1 centimeter over there. Looking right down here, what do we see? So here's the reading for our width. I'm going to estimate it as 22.55 minus 1. That's this one over here, the delta. 21.55. And now we need to include our uncertainty. What should that be? Each of these divisions is 1/10 of a centimeter, 0.1 centimeter. Half of that is 0.05. So our measurement is 21.55 plus or minus half a centimeter. So the measurement's in anywhere between 21.5 and 21.6 centimeters. Remember with bows, what did they say the width was? They said it was equal to 216 millimeters. So just a straightforward measurement that we just made right here, is that in agreement with bows? I would say definitely yes. Right? Because to go to millimeters right here, let's say to take this to centimeters, what is this equal to in centimeters? Move the decimal place once. So we definitely have it right there, in good agreement. We measure the length the same way. So like any measurement, it's going to be our best guess, plus or minus the uncertainty on the measurement. Here again, I use the rule of thumb, that it's 1/2 the least tick is the uncertainty, 27.9 plus or minus 0.05 centimeters. But that's really up to us to determine. I mean, it's a rule of thumb, like we're saying. And uncertainty is uncertain. It's such the type of thing that it's really up to you to decide what it is. I mean, we have this rule of thumb, but maybe I don't feel that confident in this, and I would say something like 20. I don't feel that certain about it. So I'd be justified to say 27.9 plus or minus 0.1 centimeters, if I like. However, we're just going to go with a rule of thumb. We're going to take the measurement to be 27.9 plus or minus 0.05 centimeters. Remember, what did Bose say about the length? They said the length of their paper is 279 millimeters. Is that the same as this? Absolutely, right? Converting metric units is pretty easy. To convert millimeters to centimeters, just move the decimal place once. Next, we're going to want to calculate the area of our paper from our sheet of paper from our measurements, including the uncertainty. And by including the uncertainty, we're going to see how the uncertainty is really behind the rules for significant figures. It's what's driving them. So the basic rule for when you're multiplying two numbers together is that you keep the sig figs you can express is the least number of sig figs in the dimensions of what you're calculating. So if your length has 2 sig figs and your width has 5 sig figs, you can only keep up to 2 sig figs in your area. Okay, so let's just do the calculation of the area, including our uncertainty, and we're going to see how this rule comes about. So how do we calculate the area of something rectangular like a sheet of paper? We know that that area is equal to the length times the width. However, if what we have is our best guess on the area, then really what we're going to be calculating is our best guess of the area from these two numbers, our best guess on the length times the best guess on the width. The area that we get from our calculation is our best guess for it, plus or minus some uncertainty on the area. But what is that uncertainty? We're going to see that this uncertainty on the area is driven by our uncertainties of the base quantities, length and width, that go into the calculation. So holding on to all of our uncertainties, you can probably see that the uncertainty on the area is contained in this calculation. Here we have plus minus length, plus minus width. These plus minuses represent uncertainties. How shall we handle them, though, in this calculation? If we keep the plus signs for both the length and the width in the calculation of area, then we're going to get an area that's as big as it could be considering our uncertainties. It'd be the largest area within our range of uncertainties. Let me call it AM for A max. So what would that be? So the largest our area could be would be the case when we take our best guess and add the uncertainties for each of those cases. Let's go ahead and expand this guy out here. Now let's look at here these last two terms. We're going to have the uncertainty on the length times the uncertainty on the width. And as you may recall, these guys are both pretty small. So this is like 0.05 times 0.05. Compared to every other number in this calculation, this guy here is super small. We might as well just toss him out. We can see over here, this A max guy is what? It's our best guess for the area, A bar, plus all this stuff. So the maximum area we have is equal to our best guess on the area plus these two factors involving the uncertainty plus something really small. We're just saying is order 0 compared to everything else. I think you may be able to tell that these factors right here, these two terms represent the uncertainty in the area. In fact, let's write it like this. The maximum possible area minus our best guess on the area we could take to be the uncertainty on the area. Right? Even though we considered only the plus case, we could consider this to be roughly approximately the plus or minus size of our uncertainty on the area. That is, our reported area is going to be our best guess on the area plus or minus this amount, which is equal to, so it's equal to our best guess on the length times the uncertainty of the width plus our best guess on the width times the uncertainty of the length. Okay, great. What can this do for us? Well, if we want to handle this in a nice way, what we can do is divide both sides of the equation by our best guess on the area. And what's that going to do for us? The uncertainty of a quantity divided by our best guess of what that quantity is known as the fractional uncertainty, or frac-unc for short. So the fractional uncertainty of our area is the uncertainty of the area divided by our measured value for the area, which is our best guess on the area. So we've divided both sides by the area. And notice again, the area is equal to length times width, and our best guess on the area is equal to our best guess on the length times our best guess on the width. You can see why we wrote these in this way on this side of the equation. Look at the terms that cancel out on the right-hand side of the equation. This is to say, the fractional uncertainty on the derived quantity of our area is equal to the fractional uncertainty of the measurements that went into it. That is, it's equal to the fractional uncertainty of our width plus the fractional uncertainty of our length. And if you want it as a percent, just multiply by 100. So the fractional uncertainty times 100 is just equal to the fractional uncertainty expressed as a percent. So this is really telling us now how to get the uncertainty on the area. Let's go ahead and put in the numbers, see how it works out. So our best guess on the area of our sheet of paper is 601.245 centimeters. How many sig figs should I be able to keep? According to what I'm seeing here, I should be able to keep 3 because 3 is the most I have on any term going into the calculation. But let's see how that holds up when we consider the uncertainty on the area. So how do we calculate the uncertainty on the area? The fractional uncertainty on the area we can see from the equation up here, which just tells us that the fractional uncertainty of the area is equal to the sum of fractional uncertainties of the terms that go into its calculation. That is, the sum of fractional uncertainties of the width and the length. So just solve for the fractional uncertainty of the area right here. That is, multiply both sides of this equation by our best guess on the area, A bar. This is what we get. So now we can just plug in to figure out what our absolute uncertainty on the area is. So now we'll just go ahead and calculate this out with our calculator. So the uncertainty on our area is equal to 2 centimeters rounded. It actually came out to be 2.47, but uncertainty technically can really only have one sig fig. So now we would report our area 601 plus or minus 2 centimeters squared. And here we can see we were forced into 3 sig figs only, right? Because the 2 is kicking on the doorstep of this 1 right here. So what we've given here is a clear example of how the uncertainty controls the amount of significant figures we can properly specify in a result or keep in a result. We had 4 sig figs going into the width of the calculation and 3 sig figs on the length of the calculation. When we kept track of all the uncertainties, we derived that the uncertainty of the derived result is the sum of fractional uncertainties that go into the derived quantity. And that limited the precision to 3 sig figs in the calculation, which exactly corresponds to the rule that you keep the least number of sig figs in your derived quantity as are in the smallest sig fig quantity that goes into the calculation. So in that case here, it's the length at 3 sig figs. Now we have everything we need to calculate the density of our paper, that is the area density, and then we'll be in a position to verify whether that density corresponds to the density given to us by the manufacturer of Bose, and whether or not we need to call them to raise Cain and Bose for giving us a bad batch of paper. We'll see. Okay, what do we got? The basic form of the density, area density, is the mass divided by the area. So here's going to be the mass of our paper divided by the area. The mass of our paper we measured as 2,300 plus or minus 30 grams, and the area 601 plus or minus 2 square centimeters. But what were the units for the area density that the manufacturer of Bose gave us for their paper? Remember, they gave it to us in grams per meter squared. So if we're going to calculate an area density in grams per meter squared, we're going to need to have our area not in centimeters squared, but in meters squared. So how can we do that? By using a conversion factor. Conversion factor is that 1 meter is equal to 100 centimeters. That is, there's 100 centimeters in a meter. However, since I want to convert centimeters squared to meters squared, I have to square this magic 1 right here. It has to be squared. When we do that now, this square will map on to every term inside the parentheses here. This become meters squared, centimeters squared, but then 100 has to be squared. So that's like 10 to the 2 squared, which is 10 to the 4. So the area in meters is 0.0601 meters squared. Great, we're ready to do our calculation of area density. Great, so will this do the job? Our area density, sigma, is mass divided by area. That's 2,300 grams divided by the area of a sheet of paper, 0.0601 meters squared. But what will be the problem with that? This is actually the weight of what? 500 sheets of paper. And how much area is in 500 sheets of paper? 500 times more area there is than in one sheet. So in order to get this right, I have to multiply by 500 downstairs here to account for the fact that there's 500 times more area in 500 sheets of paper. Now we just need our calculator. So running through the calculation, I get the area density of our paper is 76.54 grams per meter squared. Is it time to call Bose? Bose said it should be 75 grams per meter squared. Clearly, we're getting of a higher density than that. So that's one thing. I'm already feeling like maybe I should call him. Another thing is, what about our uncertainty? Do I really get to keep 4 sig figs? I mean, I just arbitrarily assume 4 sig figs. In my calculation, what do I have? 2 sig figs here, 3 sig figs here. How many sig figs do I really get to keep? Well, and what about the uncertainty of the measurement? Remember now, the uncertainty of a measurement for a derived quantity like this, whether I multiply or divide, the rule for it is the uncertainty of the derived quantity is the fractional uncertainties. The fractional uncertainty of the derived quantity, that is the sum of the fractional uncertainties of the quantities that go into the calculation. So what we're saying is the uncertainty is going to be the fractional uncertainty that goes of the quantities used to calculate them. So the fractional uncertainty is the fractional uncertainties of the quantities that go into the calculation. So here's the fractional uncertainty on the area, which is 2 centimeters squared over 601 centimeters squared. Again, since we have copacetic units, same units top and bottom, there's no need to include the units in the calculation. Same with the mass. The mass has the same units of grams top and bottom of the calculation. Since we calculated our density to be 77 plus or minus 1 meter squared, can we call Bose now and complain that they gave us a bad stack of paper or that they're giving us misinformation when they're specifying their paper? Well, I think we have to be careful right here, right? Let's assume that they're right, which is probably the case. I mean, you got to imagine that the Bose paper factory guys, they're the kind of guys that wear white lab coats and have pocket protectors, and they're pretty darn careful. All their measurements are going to be pretty careful. Maybe more careful than what I was able to do with my not so accurate scale. I'm not quite sure about it. Okay. So, this is why I can't call them.